This is the FPGA audio classification engine. A little bit of background. The 9-line medevac protocol is a universal standard used by the US military for medical evacuations. Each line gives some information and is prefixed by the numbers 1 through 9. The problem is that when these requests occur, they're generally in noisy and chaotic environments, and mishearing any of these requests can cause severe issues and possibly lead to death. So, our idea is to assist these evacuation personnel by recognizing the spoken digits in front of each line and providing that feedback to the listener. So to do this, we'll create spectrograms based off of input audio, which creates a visually descriptive image of what was happening in the audio. This is very good for a convolutional neural network, which is generally used for image processing, and it can classify these audio inputs into bins 1 through 9.
Okay, now for the technical details. Specifically, our implementation of how we're doing audio to spectrogram. We're going to be using a discrete Fourier transform, and we're going to be, after that, applying MEL filters, which is basically a type of filter that allows you to have a logarithmic y-axis for your spectrograms. The reason for this is the fundamental frequencies of human voice is 90 to 255 hertz from our research, so we really want to accentuate those lower ones using a logarithmic scale. The other thing we can tweak is our window size, so how long of a time period we're doing a DFT over. That will give you a trade-off between frequency resolution and time resolution, when we can get into that later. Moving on to our requirements, we had our environmental requirements and our microphone requirements. Our environmental requirements are going to be, having a certain level of background noise, less than 110 decibels, greater than 12 decibel signal to noise ratio. The microphone, kind of self-explanatory, but we have all the frequencies we needed. Our two main expectations is going to be portable, able to carry, and battery power, and also reliable, has consistent predictions, robust to noise, and also the processing time is going to be pretty consistent and not have high variance.
All right, so as you can clearly see with our model optimization, we ran 48 combinations here. Our model architecture, you can see this pyramid type structure, which allows us to take our inputs, you can see on the left-hand side, and sufficiently reduce that down to the point where we can run good predictions on it, on the inputs, so that we can predict digits in noisy environments. As you can see here, we have our training and validation curves. Our training pipeline here allows us to use several variables, such as early stopping, to make sure that the training and validation converge. As you can see here, initially it was like spiking, but now it converged, meaning that the validation and training match each other quite nicely, which means that we can run good predictions. And that is also confirmed by the confusion matrix. As you can see by this yellow diagonal, the train and the predicted are very much the majority in this. And here are our hardware platforms. Our GPU system, we train on an NVIDIA A100, and we were able to run inferencing on an integrated GPU on a laptop. Here's our custom kernel. Our latency ranged between and including 48 milliseconds and 77. Our power draw was relatively normal for an NVIDIA A100, and we were able to demonstrate ability to predict digits in noisy environments, digits 1 through 9.
So here we have the TPU system, where we investigated two different form factors of the TPU, one being the Coral Edge TPU USB accelerator and the Coral Dev board. Both of these contain the TPU unit on it, which has an average inference speed of 1 millisecond. And we picked this as something that would be, with a small form factor and low power draw, as well as having a very low inference speed as well. And both of these units demonstrate that, but we have the Coral Dev board is a system that allows us to do the spectrogram generation in real time on the board without any laptop support, and can happen all in one system.
We picked the D10 standard by Terasic because it has dedicated onboard memory for the model and also has an audio codec chip to help filter audio. Currently on the FPGA, we have a FFT to convert the microphone to spectrogram. We also have a MEL filter bank implemented that converts the spectrogram to MEL spectrograms. We attempted to use the Intel HLS compiler and the HLS for ML Python library to convert to Verilog for the FPGA. However, this did not work, and we would need to use an additional.
The final conclusion from our results of investigating the TPU, GPU, and the FPGA, we can see that the TPU is the clear favorite when it comes to an actual implementation for a 9-line medevac digit recognition system, as we had an average latency of 0.5 to 2 milliseconds for the TPU, power draw of 3.6 watts, and a very small form factor for the size. And comparing that with the GPU, which had a latency of 48 to 77 milliseconds and a very much higher power draw, and with the size being much larger but varying across different types of GPUs. And the FPGA, although incomplete, we can tell that the latency, although it would be similar or even better than the TPU, we could see the power draw would be greater. As even without the model, its power draw was 5 watts, so with the model it would just be much greater, as well as the size. And so therefore, the TPU was our best implementation of this system.